Hey, what's up, guys? Another beautiful day outside, another wonderful day for some geometry. So let's do this. We got our example problems from section 2.5, day one, which focused on polygons, regular polygons, non-convex polygons, convex polygons, irregular polygons, whole bunch of stuff, and specifically their angles, right? Angles hold the keys to a lot of the mysteries around these shapes and a lot of things we'll study in the future here. So like usual, we're going to do a few example problems that are on your problem set tonight. So you have this to kind of fall back on if you're finding a lack of inspiration here for doing these problems. Watch good old Mr. Fortin do these problems, and perhaps you'll find that inspiration here. Just a quick reminder, we got fingers pointing at you, but we can ignore that here. Quick reminder that we have this website here, the GOA schedule fall 2020, and I'm keeping careful track on everything we've covered, all definitions, all homeworks, all theorems, all corollaries, everything's kind of mentioned each class is here. So this is always a good thing to go back on and be like, do I need to study any of this stuff? Do I remember it all? But anyways, most importantly is that this is where you can get all your homework problems. So these are all the problems you're going to do today. I'm only going to do a few of the ones as examples that I kind of think would be good to watch if you're just like, I feel a bit overwhelmed by this. Just watch these ones. Learn how to do these ones along with good old Mr. Fortin. And then I think the rest should kind of flow okay, right? The rest of the homework should kind of flow okay. Of course, email me if you have any questions, or message me if you have any questions, or comment on the good old homework assignment that you have on Google Classroom, the post there. All right, jumping into it. 9, 11, 13. Those are some quick hitters right now. We got to sketch the polygon described. If no such polygon exists, right, not possible. Number 9, a quadrilateral that is equiangular but not equilateral. So let's think about that. Hold on a second. Quadrilateral, how many sides we have? We're going to have 4 sides. All right, we have 4 sides here. Let me switch pens. 4 sides, because it's a quadrilateral, is a 4-sided. Quadrilateral, we're going to classify that as a polygon, differentiate it from other polygons by saying it has 4 sides. So this is a 4-sided polygon. That's the definition of quadrilateral. Got to know all those definitions, right? Quadrilateral, heptagon, hexagon, decagon, dodecagon. Dodecagon's Mr. Fortin's favorite polygon. But a quadrilateral is 4-sided. It's equiangular, okay, but not equilateral, okay? Equiangular, what's that one referring to? Is that referring to angles, or is it referring to sides? This is the angles. We see ANGU, so we're going to have 4 congruent angles, okay? 4 congruent angles. What do we know about quadrilaterals too? How many degrees are in a quadrilateral? Well, quadrilateral is 4 sides, so if you do n minus 2 times 180, that's 4 minus 2, which is 2, times 180. We know we're going to have 360 degrees. So they're going to add to 360 degrees, okay? They're going to add, this is my add button, going to add 360 degrees. I divide that by 4 to figure out what each angle measures. So 360 divided by 4, that's right. 36 divided by 4 is 9, so that's got to be 90 degrees. So each angle is 90 degrees, and so do we know, perhaps from your elementary school or your preschool, right? So maybe they're not talking about 90 degrees. What are you talking about these shapes here? Each angle is a right angle, would be 90 degrees, right? That's a right angle right there. Each angle is a right angle, but we're not equilateral. Equilateral, right? When we see lateral, we think of sides, right? When we say lateral, we think of sides, right? Lateral motion is going from side to side. I'm moving laterally, right? You'll hear people say that on the soccer pitch, right? Let's move laterally, right? Don't go up and down the field, go laterally, side to side. Anyways, lateral means sides, right? So it's not equilateral, so that means we don't have 4 equal sides, but we have 4 equal angles because it's equiangular. They're all 90 degrees. I think you hopefully, great Scott, I hope you've got it. Something like this. Boom, boom, boom. What kind of shape is that? What am I trying to draw? Right angle there, right angle there, right angle there, right angle there. So I'm going to go with a non-square rectangle. There's my answer right there. Okay, so you just got to find the situation that's being described right here. I got 4 sides. Sure, those are congruent, but these aren't congruent to those 2. So, right, they're not all, and we're good to go, I guess. Let's move on. Anyways, pentagon is equilateral, but not equiangular. So, all right, we're kind of thinking visually in our heads, a regular polygon. Let's see how I can draw this so quickly over here. This is a regular polygon, a regular pentagon specifically. Remember, pentagon is, you got to know the definition for pentagon. Penta is sort of the prefix that means 5. And what is that? That's Latin, huh? So we got penta, talking 5 sides here. That's 5 sides, a pentagon. So pentagon technically means 5 angles, right? Gon is actually Latin for angles. But anyways, it'll have 5 sides anyways. So it's not this, right? Because this is regular, right? Remember, regular means both equilateral and equiangular. But here, it's not equiangular, okay, not equal. So we need to have congruent sides, which this one has here, but the angles, right? We got to have some angles that aren't the same. So I'll put some X marks right there. So you got to think about maybe what this looks like here. I'm going to go to your homework, right? I'm going to go to your homework yesterday. I stole this problem for the exit ticket. This guy right here. Let's look at this one. So this one's definitely not equiangular. That's the point of number 8 here, is you got to find the measure of the other two angles that are not 90 degrees here. So this one's 90, that one's 90, that one's 90. You got to figure out those two. But it's pretty close to being equilateral. Looks like that side is about the same as that side. This side's a little shorter than that side, that side. Do you think we can change this to be equilateral? I think we can. So you just got to be creative on problems like this, right? That's what it's all about, baby. It's all about. So let's do this here. Let's maybe do this here. I'll maybe go 3 across. I'm going to go 3 down. I'm going to go 3 down here. And then we can just eyeball it, right? Eventually you'll be able to prove, right? Those are about the same lengths. I don't know. We'll say here, right? That's about the same lengths. This is about the same length. So that's what I tried to draw here. I didn't really draw that well. I'll actually break into my geometry teacher hat and get you a perfect, perfectly equilateral pentagon that's not equiangular, because I know the underlying math with it. And we're doing with a 5-unit sides. All sides will be 5 units. So let's do it here. So I want you to have grid paper because it's easier to sketch things more clearly and calmly. And you stay sane by looking at it. You stay balanced here. Okay, I'm gonna go over 5. I'm gonna go down 5. 1, 2, 3, 4, 5. And I'm actually gonna use the Pythagorean theorem here. Pythagorean theorem to get another 5-sided figure here. So anyways, if you don't know the Pythagorean theorem, it's fine. We'll learn that in chapter 6. We'll derive it. We'll prove it. You get lots of practice with it. But I'm gonna use the Pythagorean theorem. I'm gonna go over 1, 2, 3. And I'm going to go down. Wait, hold on. That's not going to work. It's not going to work. Anyways, it's not going to work. It's not going to work. Because I can only go over 2.5. I can only go 2 or 2.5 anyways to do what I'm trying to draw. Anywho, so I'm going over 2.5, so you can ignore what I said earlier. 1, 2, 3. I was going to go over about 4, so it should be around here. And these, look at these, are about the same length. I would say about the same length here. And then over here, it's about the same length. So you can't really prove that they're the same length here because I'm just kind of eyeballing it. But yeah, they're about the same length. All right. So this is clearly not equilateral, right? Sorry, this is definitely equilateral, right? Lateral, angular. There's a lot of words. You got to keep up in geometry. Focus on the language here. It is equilateral because all the sides are the same. Is it equiangular? No, because this angle and this angle clearly aren't the same. That was the point of the exit ticket yesterday. This is 90-degree angle. That's 135 degrees. Right, based on the problem that we had earlier. Or maybe it's actually probably not 135 because this doesn't look like a 90-degree angle anymore. How about that? All right, number 13. Let's do number 13 here. We got a regular polygon, one of whose angles has a measure of 110. Can we draw this? We haven't gotten to this yet. It says not possible up here. Okay, these problems here, possibly some of them will not be possible. So let's see, a regular polygon, one of whose angles is measured 110. So maybe you start sketching it out here, but I'm kind of wondering because I haven't seen right in our practice yet. We've kind of noticed we did this yesterday during a lesson. Did we see that 110 number? Did we see that 110 number? I don't know. I just don't know. Let's check it out. Let's inspect it real quick. And perhaps that 110 number is not possible. It's not possible here. So let's see here. A regular polygon, one of whose angles are measure 110. So for a regular polygon, we need to have, right? Remember, regular, okay, is equilateral. You guys all nailed this on your exit ticket, or perhaps you just copied it and didn't really think about it. It's got to be equilateral, and it's got to be equiangular. Okay, and we don't know how many sides it has, so let's pretend that this is an n-gon. Okay, an n-gon, an n-sided figure, because n is unknown, right? N is a variable, unknown. So perhaps we need to figure out how many sides it has here. And here's how we can do that, right? Here's how we can do that. So remember that this is a regular polygon, okay? So we have a formula. Because a regular polygon is equiangular, right? Because a polygon is equiangular, we can use this formula, okay, for determining the measure of one angle based on how many angles there are. Okay, so check this out. I got this formula right here. Let's check it out. See if we can figure out where it came from. Your book doesn't really explicitly tell you this morning, but it is a formula here. They do n minus 2 times by 180. That's the big formula that was on your lesson yesterday, okay? Remember, n minus 2 times 180 tells you the measures of what? The measures of all, the sum of all the measures of the angles in that particular polygon, okay? So that tells you all of the interior measurements. Again, all n of those angles in the n-gon right here. But in this problem, only one of them, right? Each one measures 110. So to go from all the measurements, right, which is n minus 2 over 180, to what just one measure is, we need to divide that total amount, the sum of all measures, by the number of angles there are. Okay, the number of angles there are. So here we have a formula. This problem here, I would use this formula right here to determine, well, first of all, how many sides are we talking about here? How many sides are there going to be if each measure measures 110? So it says one of whose angles measures 110. If it's a regular polygon, then all angles, okay? All angles measure 110, okay, 110. So we can use this formula by saying 110 would have to equal the sum of all measures of the angles divided by a number of angles there. That's got to have to equal 110 because that's the calculation. That's what you do here. Anyways, so I did that a little fast. Maybe back and rewatch it. Think about it. Ask me questions about this here. You just need to solve this equation to determine the number of sides, right? Number of sides here. So what I'm going to do to solve this equation, this is really messy here. I apologize for that. So I didn't give myself a lot of space, but hey, we got to push forward, right? We got to keep going. I would solve this equation when you have a variable in the denominator, right? This is the way that I solve equations like this in Algebra 1. When I have a variable in the denominator, what I do to both sides to get n out of the denominator, you don't like having variables in the denominator because you want to solve for that variable. So what you got to do is, what's the opposite of dividing by n? Multiplying by n, okay? So I'm going to multiply both sides by n, okay? Both sides by n here. This whole side here was originally being divided by n, so multiplying by n will cancel that division, okay? If I'm dividing the whole side by n, and then I multiply it all by n, it's just going to become what's in the numerator up here, okay? Here we have n times 110, so that is actually, right, we're going to just distribute that n to the 110. We're going to have 110n, okay? So this is going to become 110n equal to n minus 2 times by 180. And now we just need to solve for n here, okay? So we have 110n. So here we're going to have 180n, it looks like, once we distribute. So distributive property of multiplication over addition. Distribute that 180 in there, and I'm going to get 110n equal to 180n minus 360, okay? And then what I'm going to do is I'm going to subtract 110n from 180n. I'm going to move everything up here. Sorry, guys, it's getting so messy right here. So here, I'm going to subtract, right? I'm going to take away this 110n, and I'm going to take it away from that 180, and that's going to be 70n. And that's going to be equal to, I'm going to add the 360 to both sides. Now 360 both sides, and I get 360 right here. Okay, so if I'm trying to determine the number of sides we have here, this is how I'm simplifying this equation. This is what I got right now. 360 equals 70n. What's the number of sides? I got to divide both sides by what? I got to divide both sides by 70. And let's see what happens when that happens. Guys, what's 36 divided by 7? Does 7 go into 36? Let's see here. Well, we have 360 divided by 70. And I get this. Wait, hold on. This polygon has how many sides? N is about here. What's unusual about this? What's a little like strange about this whole thing? And anyways, right? This is impossible. A polygon can't have 5.14 sides. That's crazy, okay? So there is no regular polygon. So my answer here, and I'm getting super messy with it. Let's do it in purple here. There is, what am I supposed to write? I'm supposed to write not possible, okay? Not possible. All right, there's my answer. Not possible because no regular polygon has an angle that measures 110. Okay, there's no way we could do that because you'd get a decimal for your n here in this formula. 5.14 minus 2 times 180 divided by 5.14. That's how we got to 110. But no polygon has 5.14 sides. So the sides of polygons got to be whole numbers, right? Triangle's got exactly 3 sides. Quadrilateral is exactly 4 sides. Pentagon is exactly 5 sides, okay? Hopefully you get that, right? That's sort of like some classic standardized test questions, sort of get you to trip up here to see kind of if you're understanding contradictions within questions, that kind of thing here. So that's what I kind of why I wanted to walk you through that one. 18a, what is the measure of each interior angle of a regular pentagon? Fantastic. We can just use that formula that I just showed you on the last one. Let's freaking do it. Okay, let's do it here. All right, so each angle, so this is what I was talking about earlier here. We got to get the formula. I'm going to recopy this whole thing that I just said here. Formula for determining the measure of one angle of a regular polygon. Okay, you want to have that in your notes. Okay, you have the formula for containing the measures of the sums of all angles of any polygon, any convex polygon, and that was a theorem, but they don't really talk about this one here. This is sort of extends. It's almost like a corollary of that theorem. So you easily prove it because you have this many sides and it's regular. All equal angular, here, this is your answer. So anyways, I'm not going to write the formula because the formula is up here, okay? So I'm just going to substitute the 5 in here. Remember, pentagon has 5 sides, okay? And therefore 5 angles. So we're going to do 5 minus 2 times by 180 over 5, right? We're just going to take how many degrees are in a pentagon, which is 540, right? You should be trying to memorize those. Quadrilateral is 360. Pentagon's 540. Hexagon is what, 720? Is that right? Yes, that's right. And octagon, man, I'm forgetting what octagons are. Man, you figure it out. Is it 900? I don't know. Anyways, I guess 900. I don't know. No, maybe more than that. 1080? I guess. It's all good. It's all good. You try to memorize as much as possible, but then also do the math. You got to get it here. All right. Anyways, 3. This becomes 3. And 3 times 180 is 540. Okay, so we got 540 divided by 5, and 540 divided by 5. Well, 5 goes into 500 100 times. 40 goes into 48 times. So 108 degrees. Okay, so I got 108 degrees here for the measure of one regular pentagon. Can you tile a floor with shapes like regular pentagons? You might be wondering what the heck this tiling is about here. I got my floor tiled. My dog is a mess, so there's a bunch of dog fur down here. But check it out. My floor is tiled with rectangles. These are rectangles right here. Okay, check it out. Give Mr. Ford socks here. So rectangles, you can tile it. So what tiling means is taking up all the space, right? I can't tile my floor and leave the barren ground below it that the builders put in, right? We want to tile it so we can walk through it nice and smoothly. So here's a tiled rug design right here. This is really beat up by this dog right here. Yes, this dog is a mess, pulling all that dirt. So these look like parallelograms. You can tile with parallelograms. Look at all the space is taken up. There's no open space here. So anyways, the question is, can we tile with regular pentagons? Let's check it out here. I got my regular pentagon tool. I got it. Let's check it out. Let's do it. Pentagon there. Pentagon everywhere. So I'm going to see if I can like copy paste maybe. Let's see, that might help me here. Ooh, I got another one. Very good. Let's get another one. I think I'm just going to need 3. Trying to paste you. It's not working here. All right, here we go. This one. Oh, it's all twisted around here. Here, I want to move it here. Okay, let's see if I can tile it. Okay, so I'm trying to take up all the space. Maybe rotate this here. Maybe I'll put that there. Okay. So another way we think of tiles is these squares are tiling the grid paper, right? It's taking up all of the planar surface, right? That's what tiling is taking up all the planar surface. We're taking up all space, perfectly tiled the plane, right? Tiling the plane, tiling something to do the plane. So let's take this one here and let's see if we can tile this over here. Let me move it. Oops, whoop, bigger one. So they don't say it needs to be the same size, but I'm going to try to make it the same. Oh, let me just delete that one maybe. And then let's move this. Okay, move it down here. Can I tile this? And let's try one more. Can I? Ooh, what's the problem here? Can I? Looks like I can't tile this, guys. What's the problem with tiling in this one here? Who knows? Who's maybe studied this a bit before? It's one of the nice thing in class because you just be like, oh, who studied this? Who knows why? So I can't tile this. Look, I'm trying to tile it. And oh, okay. If I had a parallelogram there, maybe there'd be a parallelogram tile there. But you know what? We have this open space. We can't just do this with regular pentagons. Okay, so let's take a look at this here. Do you notice this open space? Okay, so right here, this right here. Okay, you could tile something with pentagons and parallelograms. It looks like. Okay, so here this is not a regular pentagon. So our answer here is no. We can't. And why, right? Why was I able to tile things with rectangles, with parallelograms, which is my rug, and I could also do it with pentagons and parallelograms at the same time. But for this one here, no, no, we cannot. Come on. Open this up a little bit here. Come on, people. You're like turning off your YouTubes right now. Here you go. No, we cannot. Tile only using regular pentagons. Yeah, but why is that, right? Why is that? Well, we couldn't fill up the space here, okay? What does that have to do with this? What does this have to do with part A of the question? You should be asking yourselves here. Well, I got 108 degrees. Why did that then lead to the fact that, well, if this is 108 degrees, this is 108 degrees, and this is 108 degrees, why did that make it so we couldn't tile up the floor? I'll save it for you. We'll maybe go over that one tomorrow in class if you don't get it here. Okay, 2 more to go in 25. Hey, I might not talk about that one very much because look at this. Ooh, ooh, ooh. Okay, just getting word out there in that one. Now we got number 21, which is about a regular decagon. My second favorite shape, I guess. Oh, no, never mind. I don't really have a second favorite shape, but the dodecagon. All about that dodecagon. Anyways, regular decagon. Okay, so what we're going to know about that, the intelligence we get from the name is that a decagon is a polygon. That's why it's the definition from yesterday. Decagon is defined as a polygon, right? Classify it, differentiate it, it has 10 sides. Okay, so this is a 10, not 16, 10-sided polygon. And if you remember it here, if you remember from the lesson, the vertices got to be consecutive. Okay, we got to go going around the 10 sides. We'll have 10 angles, and therefore 10 vertices. And we got to go in this order, okay, this order. So we have a segment AB and we have a segment BC. Look, we have a segment BC, but then we have a segment CD, okay? Then we have a segment CD, and then so on and so forth, okay? So this problem is going to deal with sides AB and CD, okay? So I'm not going to draw the whole 10-sided figure because it's a regular decagon. We maybe find a shape that looks like that online and paste it here, but I'm not going to do that, or maybe I can. Ooh, does it let me go to 10? It does not let me go to 10 in the tool here. Oh wait, well, no, won't let me go to 10. Anyways, so I'm just gonna kind of sketch out a few of the sides here. Okay, so the ones we need to be concerned about are A, B, and C, D. But look, we go from vertex A to vertex B to vertex C to vertex D. So what we haven't mentioned yet is that there is a side BC right here. Side AB, side BC, side CD, side DE, side EF, side FG, side GH, side HI, side IJ, and finally side JA would be the 10 sides of that regular decagon, okay? 10-sided polygon here. So I'm just going to draw 3 of the sides here because this just has to do with side AB and side CD, but also BC is the side in between those here, okay? So maybe I'll just sketch it real quick. One side, another side, and again, we don't know exactly what this looks like. It's hard to draw a decagon. That's why we need to do constructions. We probably won't do this here. Anyways, okay, so let's just say that this is A and B, and we know that the way that the polygon is named, those are consecutive. So A goes to B goes to C next, and C goes to, and I'm trying to draw it so the angles are roughly the same. C goes to D here. And I'm trying to draw it so that, right, you know that these sides are all the same because it's a regular decagon. Okay, so if we kept going around, right? We might have 10 congruent sides with 10 congruent angles all the way back here. But this problem all cares about AB and CD. We got to extend it to meet at K, find the measure of K. So I think AB, line AB and line CD will intersect. Yeah, will intersect. And they're going to intersect somewhere outside. So, right, our decagon is here, right? This is the interior of decagon. Oops. My stylus is not plugged in. There we go. Interior of decagon. So if we're going to extend, okay, we're going to do this. We're going to extend this CD and AB to intersect. We got to extend in this direction. We're going to extend this segment over here, and we're going to extend this segment over here. And they intersect with one another. They meet at point K, okay? And this is the thing, is that I think they say find the measure of angle K. The way that I drew this diagram a little confusing is that we have 1, 2, 3, 4 angles at point K right here, the way I drew this diagram. So there is no angle K in this diagram. I need more information than that. I have an angle BKC, but I don't know what to name those angles here. So I'm going to erase this briefly right there and right there. And I'm going to have the points, I'm going to have the segments end at point K, terminate at point K. Then it'll be pretty clear what angle K is, because there'll be only one angle K in the diagram, okay? So I'm going to extend this way. Oops. That's too. Maybe I'll do it so I get a straight line. There we go. There we go. That's what I wanted. Okay, right at K. Terminates at K. The segment terminates at K. Segment terminates at K here. Okay. Anyways, so these segments here, let's pretend, yep, this is on AB, okay? This is CD here. So we still have segment AB here. We have segment CD right here. And the question mark is, we got to figure out this. We got to figure out what this equals. What the heck that equals here. Okay, how can we figure that out? Well, if we extend into point K, we have what kind of a shape? Ooh, what do we see here? This is a, oops, no, not a circle. That's silly. I can't even undo that either. It's gonna. All right, good. Undid it. This is a triangle, people. I don't know why I made it a circle for me. So this is a triangle. So we're trying to find, oops, trying to kind of find the top of this isosceles triangle, the vertex of the isosceles triangle here, trying to find what it measures. The question is, what is that equal and what is that equal? Well, look here. Hey, it's supplementary to an interior angle of the decagon here. So if we can find this, then we can find what is the angle it's supplementary to and figure out this is this one, this is the same over here. And then this would just have to be the final angle of the three angles that all sum to 180. So that's my game plan. That's how I'm going to solve this here. So try to follow along with my logic here as I go ahead and solve this. So measure of angle, the way I'm going to do this is I'm going to find the measure of angle BCD first. Then I'm going to find the measure of BCK first. That'll be the same as measure CBK. And then finally, I'm going to subtract from 180 the measure of these two angles to get the measure of angle K. And there, I have my answer. That's about it here. So feel free to fast forward to the next problem or do it along with good old Mr. Form right here. Okay, measure of angle BCD. Well, that is an interior angle of the decagon. Okay, so we need to get the interior angle of the decagon to get measure of angle BCD. Look, this is an interior angle. This is your decagon, right? I can keep going my decagon, keep going through, but I don't need to do that. Okay, so I'm going to get this right here. And what I need to do that, interior angle of a regular decagon, that's an important thing. So I'm going to do that same thing with the formula, n minus 2 times 180 divided by n. So my n here is 10 minus 2 times by 180, and I'm going to divide by 10. Okay, and that's 8 times 180. I'm going to go to my trusty calculator for that. No reason to expend that brain space. So here we go. 8 times by 180 divided by 10, that's 144 degrees. Friends, that is 144 degrees. Okay, so we know that this is 144 degrees. Okay, that's going to help us get this one. What's this one going to be right here? Okay, so let's switch to regs. We're talking about the triangle. Well, this is an exterior angle of a decagon here. And actually, there's a shortcut to figure out the exterior angle of the decagon, because what are all the exterior angles, right? The sum of all exterior angles, one set of which of the decagon sum to? They sum to 360. How many exterior angles would be in a set of a decagon's exterior angles? Well, you'd have 10 going around because there are 10 interior angles. So what's 360 divided by 10? 36 degrees. 36 degrees. Did you get the 36 degrees already? Did you get the 36 degrees already? Well, yeah. 144 plus 36, that equals 180. So wait, remember, the exterior angle is supplementary to its interior angle, right here. But for a regular polygon, you can get the exterior angles very easily. You got to take 360 and divide it by what to get to 36? 360 divided by 10. Okay, so this equals 360 divided by n, right? Divided by n, and that's the measure of one exterior angle of a regular decagon. Okay, so there's a shortcut for you. I figured I'd show that here. Anyways, this is 36 degrees. That means this has to be 36 degrees too, because this again, oops, not 360, 36 degrees here, because this again, right, this is an interior angle right here. That's also 144. Okay, so that's got to add to 180. And now finally we can get our answer. Okay, we can get our answer because this question mark right here, that's just going to be 180 minus 2, right? Because we got 2 of the 36 degree angles, 2 times 36, and that's going to be 72. So 180 minus 72 equals 108. We get that 108 answer again. Second time in this homework, you have this 108 answer. Remember that. This is from a pentagon, regular pentagon's interior angle, 108. This has nothing to do with that. It just happens to be 108 as well. All right, last problem here. Oh, we have a finger pointing at us. Wait a second. I thought you said Mr. Ford is going to do this as an example for you. Well, is he? No, my friends. Fingers pointing back at you. Guys, this is your presentation problem for tomorrow. This is always a tricky one. I want to say usually like 20% of people kind of get this one going through. And man, I've seen some really, really good explanations of this problem and really, really good justifications. So if you think that you can explain this one tomorrow, be my guest. Go ahead and do it. I don't really want to give you any hints, okay? I'm not really going to give you hints. I could draw on this. I could show you exactly how it's done, but I don't want to do that. I want you to earn it for yourself. Just remember what's been talked about this section here, okay? We found the sum of the measurements of the interior angles of any polygon, right? Of any convex polygon. We know a formula for that. We have a formula for the sum of the angle measurements of one set of exterior angles. Ooh, okay, in a polygon for this one here. Obviously, this one is not a polygon. Okay, this figure is not a polygon, but could you find a polygon somewhere within it? Could you just break it up into different polygons? I've said too much. No, I haven't said too much. I think that's fine. That's enough to get you started in this, so that you're not totally hitting yourself again, your head against a wall. Okay, give this one. Try to work it out. It's okay if you turn in your best guess tomorrow. Doesn't have to be perfect because we'll go over this one. And if you do feel pretty good about this one, you, my friend, have the opportunity to present and earn that free homework late pass. Oh, yes, that's always good to have that in the bank for the rest of the semester. And that's it. Okay. Email me if you have any questions. Message me as you're trying out more of the problems. If you have those burning questions that you don't want to wait until the Jamboard to review tomorrow, please reach out and I can definitely help. Have a great day, Tuesday, guys. I will see you guys tomorrow.